world of integrals 3. We have seen the extension of Riemann integral to Riemann-Stieltjes and Lebesgue-Stieltjes integrals. Also, we have discussed some properties of Riemann-Stieltjes integrals and two very important and interesting theorems. One is Helly's theorem and Helly-Bray theorem, which actually connects the integrals with the sequence of functions and deals with the existence of the limiting form, or under what conditions we can get this limits of integrals of sequence of functions, rather the Riemann-Stieltjes integral of sequence of functions. Now, today we will discuss more or less the same thing, some more theorems and two very interesting concepts, like if I want to integrate, if I want to differentiate the integral, can we change the order of differentiation and integration? That is a very basic question in calculus, and we can discuss this same question under the paradigm of probability theory. Similarly, suppose there are two integrals or so called double integrals, one with respect to variable say x, another with respect to say variable y. The question is, can we change the order of integration? So, we will be discussing these very important concepts in this class. We know two important theorems, one is Helly's theorem, another is Helly-Bray theorem, which is the extension of Helly's theorem to infinite intervals. But note that one interesting feature here, the function with respect to which we are integrating, we considered a sequence of functions, but the function which we are integrating, that is g x, which is same, which does not depend on n, which is not a sequence of functions. Now, the question is it possible to consider just a reverse situation, like when the integrand, the function which we are integrating is a sequence of functions, and the function with respect to which we are considering the Riemann-Stieltjes integral is a function which is not depending on n? Can we get some theorem analogous to Helly-Bray's theorem? The answer is yes, and to that end we have what is known as bounded convergence theorem, because by this time it is quite understood that all these theorems should hold, if it at all holds, or if there exists such a theorem, they should hold under certain conditions. So, let us see what are the conditions under which this bounded convergence theorem holds. Suppose g n x is a sequence of functions whose limit exists as n goes to infinity, and at the same time modulus of g n x less than equals to g x for every n greater than equals to 1. That means, this g n x function, although depending on n, or rather the g n x, this sequence of functions is always bounded by another function which depends only on x, but not on n. So, it is a function independent of n. So, this function, modulus of this function is bounded by another function which is just a function of x, and for every x belonging to a to b closed interval, we assume that g x must be integrable, this capital G x. That means, the function which gives a bound to the sequence of functions must be integrable with respect to another function df, another function capital F x within the interval a to b. Now, this capital F x usually considered as a distribution function. Then we say that g x is integrable with respect to capital F in the interval a to b, and we have this famous theorem that limit n goes to infinity of this integral a to b g n x d f x equals to limit integral a to b g x d f x. That means, when we integrate this sequence of functions with respect to capital F x, as n goes to infinity, this converges to the integral or RS integral with respect to f x of the function which is nothing but the original limit of the original sequence of function, that means g x. So, g x is the limit of this sequence of functions, and this has been incorporated here. So, this looks quite natural, and so we are going to explain this using an example. Now, suppose g n x is a function which is e to the power minus of x plus 1 by root n. Naturally, if you take the limit with respect to n, then this goes to this 1 by root n goes to 0, and hence g x is nothing but e to the power minus x. We can easily take capital G x as e to the power minus x. You can take any other function which gives a bound of this, but which should be integrable with respect to capital F x. So, the question is, what is our choice of capital X? Let us take capital F x equals to 1 minus e to the power minus x divided by 1 minus e to the power minus 2. If we take the interval a equals to 0 and b equals to 2, incidentally it is seen that this capital F x is nothing but the distribution function of an exponential random variable which is truncated at x equals to 2. That means, consider an exponential random variable, an exponential distribution, but x lies between 0 to 2. So, this is truncated at 2. So, if we consider that, then the distribution function can be given by this. Naturally, it is a non-decreasing function. Now, according to this bounded convergence theorem, we can write this limit of this integral equals to this integral. So, let us calculate this integral first, then take the limit, and let us see what happens. So, if we just calculate, put g n x as e to the power minus x plus 1 by root n and d f x as this, and if we calculate this integral, it is very easy, it is a very standard integral, and it can be shown that this goes to this integral, and incidentally this integral is exactly equals to a to b g x d f x. So, that means mathematically, if all these functions, because this function satisfy all the conditions of bounded convergence theorem, so naturally this should hold, and just by calculation, that means calculation of left hand side and also calculating the right hand side, we see that these two are equal. Now, we will demonstrate this using some diagrams. So, this is our choice of g n x, g x, capital G x, and so on, and this is your capital F x. Then we plot g n x here and g x in the vertical axis, capital F x in the horizontal axis, because we are going to consider Riemann series integral of g n x or g x with respect to capital F x. So, capital X should be plotted in the horizontal axis. Now, suppose n equals to 1, then if we look at this area under the curve g n x with respect to capital F x, this is the red shaded area which is given by the integral of g n x with respect to capital F x when n equals to 1, and this is the limiting integral, that is integration g x with respect to capital F x. But you see, these are really, they are not converging. So, there is a substantial portion which is only red, but there is no gray shade. Now, consider n equals to 3, and immediately we see that this substantial portion which is only red drops to this portion, but still there is some portion which is not covered by the shaded gray shaded region. So, what happens when we increase the value of n? Suppose n equals to 20, and it is clear that it starts converging. So, as from n equals to 3, as n increases to 20, this portion which is only red, but not shaded by gray, it drops down, the area drops down substantially. And what happens when n equals to a very large number? It should converge, right. So, suppose n equals to 200, and we see that they almost converge. So, now if we increase more the value of n, then almost there should not be any difference between these two. So, both will merge. So, this gives a nice pictorial representation of the convergence according to the bounded convergence theorem, because it is the functions that we have taken and the function with respect to which we are considering the RS integral or Riemann-Stieltjes integral, they all satisfy the basic conditions of the bounded convergence theorem. So, whatever we are getting by numerical method, we can also demonstrate the same thing using graphs. Now, we consider another important thing, that differentiation under the integral sign. So, let us first state the theorem. So, if for continuity points of x of function g and for a fixed value of t, the partial derivatives of g x t with respect to t exists, and second condition is this modulus of this partial derivative, this is mod of del t of g x t is less than equals to g x. Now, naturally, this should be independent of t, which is this g x is again should be integrable over the entire real line or over the interval on which we are integrating. Then, if we consider the integral of g x t with respect to, or Riemann-Stieltjes integral of g x t with respect to capital F x, and then differentiate it with respect to t, note that this here the during the integration is with respect to the variable x, but the differentiation is with respect to another variable, that is t. So, first integrate and then take differentiation, which must be equals to, if we insert or if we take this differential sign inside the integral sign, that is integration of del t of g x t with, and then we consider this as an integrand which we integrate with respect to capital F x. So, this gives us a nice way to sometimes to integrate some complicated functions. Suppose one nice example is, one nice situation might be, example of a situation like might be that g x is slightly complicated, but when you differentiate this with respect to t, that function becomes relatively easy in order to integrate that function with respect to capital F x. Because sometimes it might be possible that this g x t is slightly complicated, or rather too complicated to integrate with respect to capital F x, but if we take the differentiation of g x t with respect to t, that function becomes relatively easy to integrate with respect to capital F x. Then if we see that these conditions hold, then these two are exactly same. We are demonstrating this using a numerical example, or rather algebraic example I should say. Suppose g x t equals to e to the power minus t x, capital F x equals to 1 minus e to the power minus x. Now, again you can identify this as the distribution function of a exponential random variable over the interval 0 to infinity. Now, all the conditions are satisfied. So, let us consider the left hand side, which is integrate first and then differentiate. So, g x t is e to the power minus t x, and d of capital F x, if we just do a little bit of algebra, it will give us e to the power minus x dx, and if we integrate this entire quantity, this becomes 1 by 1 plus t. Now, differentiation of this quantity 1 by 1 plus t is nothing but minus 1 by 1 plus t whole square. Similarly, if we consider the right hand side of the previous theorem, where we can take or bring this differential under the integral sign or inside the integral sign. So, we first differentiate it. So, differentiation of e to the power minus t x with respect to t is minus x into e to the power minus x t, and d f x is nothing but e to the power minus x dx. If we integrate this, or rather if we simplify this function, this becomes minus of integral 0 to infinity x into e to the power minus 1 plus t into x, and this is nothing but a gamma integral, and using the gamma integral formula we can thus get that this entire integral is nothing but 1 by 1 plus t whole square, and there is a minus sign. So, it becomes minus of 1 by 1 plus t whole square, which matches exactly what we get on the left hand side. So, since these two functions satisfy all the conditions of the previous theorem, which says that it is allowed to bring the differentiation under the integral sign, so it clearly matches with that. So, it is a nice demonstration of the previous theorem. So, we have discussed that how to bring differentiation under the integral sign. Now, is it, or rather we can how to change the order of differentiation and integration. Now, the question is it possible to change the order of two integrals? Actually, the answer is yes, but under certain conditions, which is known as Fubini's theorem. Suppose g x t is continuous in t, where t within the interval a to b, and for every x lies between minus infinity to infinity. Again, like the same previous theorems, mod of g x t is bounded by g 1 x some function for every t belonging to a to b, and integral minus infinity to infinity g x t mod of that quantity dt is bounded by g 2 x, and these two bounded functions g 1 x and g 2 x both are integrable over minus infinity to infinity. Then we can immediately change the order of this integral. We will explain this change of order of integrals, of which is known as Fubini's theorem, using an example. Suppose g x t equals to theta into e to the power minus theta t into e to the power minus x. Clearly, we can take g 1 x as theta into e to the power minus x, and g 2 x as e to the power minus x, capital F x equals to x. Then, if we calculate this integral with respect to x first and then with respect to t, note that here x ranges from 0 to t and t ranges from 0 to infinity. So, the entire range with respect to x and t can be written in one line, like x 0 less than x less than equal less than t, which is less than infinity. That means, when t is fixed, x lies between 0 to t, and when x is fixed, t lies between x to infinity, and independently both of them varies from 0 to infinity. So, if we consider this integral first, this is nothing but theta e to the power minus theta t into e to the power minus x dx. If we just integrate it and put the limit 0 to t, we will get e to the power theta e to the power minus theta t, because this is just integral of e to the power minus x with respect to dx with respect to x, which is 1 minus e to the power minus theta t. And if we just integrate this whole quantity, then we will get 1 by 1 plus theta. Similarly, if we consider the right hand side of the integral x to infinity, here since we are doing the integration first with respect to t, then t should range from 0 to from x to infinity. So, x to infinity and this quantity, then it becomes e to the power minus 1 plus theta x, which is 0 to, when integrating 0 to infinity, it gives you 1 by 1 plus theta. So, hence this 2 actually matches. So, the Fubini's theorem is satisfied because all the conditions are satisfied here, and since we can easily use Fubini's theorem to change the order of integral. So far, we have studied today some theorems, some concepts related to integrals, mostly Riemann-Stieltjes integral. As you know that Riemann-Stieltjes integral under some special condition can be reduced to Riemann integral as well. So, whatever be the situation, now we know that we can change the order of differentiation and the order of integration only under some conditions. Now, those conditions come very naturally if we look at if we just try to write the result or the theorem, which is the changing the order of differentiation and integration. Exactly similarly, if we have two integrals based on with respect to two variables, we can also change the order of these integrals only under certain conditions, and those conditions come very naturally if we just look at the statement of the theorem. The advantage is that sometimes it would be very easy to differentiate the integrand of the function instead of directly integrating that function first. Similarly, if we change the order of integration, sometimes the integration becomes very, very easy. So, these are the main advantages of considering these two theorems.